So today what I would like to do with you is review all the major things we had with fluids. This is in preparation for your big assessment, and by big assessment I mean another 10-point assessment, but one that involves all areas of fluids. So I'd like to start with the hardest possible thing, and that would be a piping system where the elevation changes and the diameter of the pipe changes. We'll call this region 2 and this region 1, not that it really matters. Okay? And we had a formula that looked like this, which was great at describing that the velocity could change based on a difference in height or a difference in pressure. We could rewrite it instead of using the deltas, using P1 and P2 and H1 and H2. This is not really helpful, but it actually is very helpful if we get rid of all the negative signs by bringing all the things involving pressure 2 to one side and all the things involving region 1 to the other. So this is a great way of visualizing why things have their speeds change. This is great in terms of solving problems. It consolidates everything about region 1 and region 2 to one side of the equation. So all the stuff for region 2 goes in there, all the stuff for region 1 goes in here. So you need to know the pressure, the velocity, and a height from the ground or from wherever you want to measure the height from. Again, make sure you measure your height from the same spot. Velocity 1 and pressure 1. Okay, so to summarize, solving problems, it's nice to write it this way. Figuring out why it's actually changing speed, it's nice to write that way. So let me show you how we could solve problems using this crazy formula that we just got. We already know the answer to this, and we took a lot of time deriving this answer, but I'd like to show you how we could do it using this big equation. So we have region 2, and then region 1 would be up here. I picked this as region 1 because we know the pressure here is atmospheric pressure pushing down on region 1. We know the velocity here is 0. Okay, the pressure here is atmospheric. Region 2, this is also atmospheric. Because region 1 and region 2 were picked in such a way that they're both atmospheric pressure, we can get rid of them. I would pick this as ground level so that the height of region 2 is 0. That would get rid of this whole term. Velocity 1 is pretty much 0, because if it's a big enough tank, this water's barely going to be moving. After getting rid of all the things that don't matter, we're back to 1/2 rho V2 squared equals rho GH. Density is on both sides. We can cancel it out. And we get 1/2 V2 squared equals GH. V2 squared equals 2GH. V2 equals radical 2GH. We already knew that. We derived it from Newton's laws. I just wanted to show you how we can get it with this equation. This one equation could solve any of the problems we did with moving fluids, so long as we know enough of the variables. Okay, so we were working on this one, or we at least introduced you to this one. And if we want to use this equation, we could pick region 2 and region 1. We would put the pressure for region 2 as 321,000 pascals. Make sure you're working in pascals and not kilopascals. Pick ground level as the center of our piping system, and then the height of each side would be 0. It doesn't matter where you pick your ground level. Both heights are going to be the same, so either way, this whole term and that whole term cancel out. Okay, the velocity in region 2 we already have. it's water, so we make that 1,000. Pressure 1, we don't know. And velocity 1, we don't know. So it seems like we can't solve because we got 2 unknowns, and that's when we resort back to the idea of continuity of flow. We know that the flow rate has to be the same in both pipes. So we do flow rate 2 equals flow rate 1. Area 2, velocity 2 equals area 1, velocity 1. So find the area of this pipe, find the area of this pipe, use the velocity on the left to find the velocity on the right, and plug it in here. That will allow you to calculate pressure 1. If all went according to plan, pressure 1 should be less than pressure 2 because the fluid sped up. Faster moving fluid is going to be the area of lower pressure. Remember that this formula only works for smooth flowing fluids. It would not work if we were using honey. Okay, I want to remind you again of the difference between our beverage container and our faucet. Remember, with the beverage container, there is a constant difference in pressure, so we have a constant velocity regardless of the size of the opening. With this system, there is not a constant pressure. The pressure changes in this part of our system as we constrict the flow of the fluid. So this will not have a constant delta P, and therefore it will not have the same velocity when we change the size of the faucet. We saw this really well with our sink up front. We saw that when it was like this, it was not leaking, and when we had this on here, it was leaking. Again, by putting this constrictor on, we make a higher pressure. I would like to take a moment to make sure you understand something. The flow rate here equals the flow rate here. It has to. It's continuity of flow. When we look at this one, the flow rate here has to equal the flow rate here. All's well and good. Here's where I want to make sure you don't get the wrong impression. This flow rate does not have to equal this flow rate. So when we put that constrictor on there and we get a different speed, the flow rate with the constrictor does not have to be the same as the flow rate without the constrictor. We do have to have the same flow rate at any given moment. So the flow rate here is all the same. The flow rates here are all the same, but they are not necessarily the same. They are taking place under different conditions. All right, so I hope I made that clear. I want to remind you of pressure. Remember, pressure is force over area. So depending on how you orient your block, you're going to get different pressures. Having the block sit on the big surface is going to be a low pressure, and having the block on a smaller area gives you a larger pressure. So remember how to get pressure in general. Smaller area, bigger pressure if the force stays the same. I want to remind you that if we create a difference in pressure, so we got pressure 1 on one side of this milk cap, pressure 2 on the other side of the milk cap, that will create a force on the milk cap. Okay? So same equation, but this time we are having the pressure create the force instead of the force creating the pressure. Okay? So it could work in either direction. I want to remind you of Newton's second law. It doesn't just apply to objects like hockey players. We saw in this unit that it applies to things like fluids, water, and gases, right? Follow Newton's second law. I want to remind you that the force net comes from a difference in pressure. All right. I want to remind you that if you need to find the mass of an object and you don't have access to a scale, if you know the density of the object, you can find the mass by multiplying the density by the volume. And then I had a couple of problems I wanted you to try just to show that you can do this. So determine the speed of the water coming out of this tank and determine the amount of water that comes out in 1 minute. The hole has a diameter of 1 centimeter. All the information you need is here, so I'm going to allow you guys the time to work on this. If we tried doing it using this equation, which we can, this equation will work for anything. Pick your two regions. I would pick 2 and 1, right where the fluid meets the atmosphere. That makes things simple, because then both pressure 2 and pressure 1 are atmospheric pressure. Again, for heights, you can have your ground level anywhere. So if you'd like, you can measure from the ground, you can measure from the bottom of the water. The easiest would be to measure from the hole. So if you're calling this height 2, height 1 would be 0. That's always the best option because it makes it easy. You can get rid of one of these terms. You want to assume that the velocity inside the tank is 0, so you can get rid of this whole term. And then you are down to just rho GH equals 1/2 rho V1 squared. This boils back to this, okay, which you could have done in the first place. Again, I just want to get you used to this big long equation because this will work for all cases where you have a smooth flowing fluid. This only works for the special case where both the top and where it's coming out are exposed to the atmosphere. Here's another one that we haven't done before. I'd like to see if you guys could figure out how quickly the water is coming out of this fountain. This one is incredibly hard. I would never ask you to do something like this on your own. But if you're watching this video and you're not in class, I will provide for you the steps to solve this problem. You will not get anything this complicated on your test, but I just wanted to make sure you guys could see a real life example of how the pressure creates the fountain with a certain speed, okay? Which would then translate into a certain height. So if the designer of the fountain wants to get the water to a certain height, they have to set the pressure in this pipe to a certain value. So anyway, like I said, don't worry if you don't want to try this one, but I will provide the steps so you can see how this works. Anyway, I wish you the best of luck on the test. And again, the test is only worth 10 points.